Welcome to another module in our soot-free and zero-emission urban bus fleets technology transition curriculum. Today, we're taking a look at fleet-wide planning. Here are some key terms and acronyms that we will come across in this module. Total cost of ownership, TCO, which we have mentioned in earlier modules. It is a framework to look at a vehicle's cost over its service life, including not just the purchase price, but also cost of maintenance, refueling and recharging, and other costs incurred during operations. This sometimes also includes the residual value and external costs of air pollution and climate change. Baseline performance refers to the key performance indicators of current operations with the existing fleet of buses, such as energy consumption and the number of buses to serve a given route, among other things. This data enables simulations and modeling of fleet-wide planning activities. It is also a reference for soot-free and zero-emission technologies to compare against. Kinetic intensity is a measure of drive cycle kinetics, reflecting how much stop and go occurs in a cycle. It is derived from the ratio between characteristic acceleration and aerodynamic speed and measures the energy available for regeneration, which can help identify drive cycles where hybridization and electrification would offer fuel economy improvements. A representative drive cycle is a profile of real-world driving conditions along a single bus route. It comes from empirical operations data from the particular bus route and is thus more realistic. This representative drive cycle serves as an accurate model input to estimate route-level emissions of air pollutants and greenhouse gases, as well as to calculate the costs of alternative technologies at the individual route level. Finally, energy consumption modeling is a step in the fleet-wide planning process where we plug in the drive cycle information of a particular route and the technical parameters of soot-free and zero-emission buses into vehicle simulation software. It is a key determinant of the total cost of ownership and a very useful way to compare technologies and operational strategies to review which technology will perform best and at the lowest cost.
Here are the key learning objectives from this module. Understand the meaning of fleet-wide planning and its importance for a bus operator to make procurement, operational, and fleet renovation decisions. Understand how fleet-wide planning fits in and relates to the rest of the curriculum. Understand total cost of ownership as a framework for bus financing and business models. Learn the major steps involved in fleet-wide planning, how to establish a baseline performance of current fleet operations, the data inputs and collection, development of real-world drive cycle, bus energy consumption modeling, fleet-wide emission modeling, individual bus total cost of ownership assessment, and route-level total cost of ownership assessment. And to use the results from fleet-wide planning to inform procurement and operation decisions.
So far in the curriculum, we have discussed the health and climate benefits of soot-free and zero-emission urban transit, the different technologies available for soot-free and zero-emission buses, and their infrastructural needs. This module is about fleet-wide planning. In the upcoming modules, we will also talk about the pilot programs of newer soot-free and zero-emission technologies, the business models and financing options for soot-free and zero-emission bus technologies. We believe fleet-wide planning should be at the center of all of these executive, financial, and technical decision-making. Fleet-wide planning helps determine the kinds of vehicle technology, infrastructure, and operations that will deliver the range and performance equivalent to buses already in service, while extending the climate and health benefits unique to soot-free and zero-emission technologies. Fleet-wide planning isn't just a standalone component of a technology transition, but a framework through which bus operators should adopt before, during, and after the transition. An important concept throughout the fleet-wide planning discussion and for the rest of the curriculum is total cost of ownership. For bus authorities and agencies that operate conventional fuel vehicles, most business and financing models treat the purchase price and capital cost of a bus as a primary metric for cost. But when it comes to soot-free and especially zero-emission bus technologies, the old model will put cheaper technologies and products at an unfair disadvantage, since newer technologies, especially zero-emission buses, have a price premium, as explained in Module 2. We believe the right metric for cost is, in fact, the total cost of ownership, which not only accounts for the upfront purchase price, but also fuel costs and other operating costs. Zero-emission technologies have lower maintenance and operating costs than diesel and CNG buses. The total cost of ownership, which includes maintenance, operation, infrastructural acquisition, and bus acquisition, actually puts zero-emission buses at an advantage. The framework of TCO also enables alternative business and finance models to have a faster deployment of alternative technologies. Now let's move on and talk about some of the key steps in fleet-wide planning. There are three major steps. First, we need to understand the operations of buses on existing routes. Then the data from current operations, or the baseline performance, is used to generate representative drive cycles of different routes. We can then plug in different alternative technology buses through biomethane gas or battery electric to simulate the energy consumption, the range, cost, and replacement ratio compared to what's currently operating. This information is very useful to plan the purchase of new buses and which routes they should serve on, as well as the infrastructural investments that would need to be made for the new plan to work. Let's now go through a few steps one by one, starting with the most important collection of current operations data. First, operators should understand the performance and efficiency of the buses currently in service. This is called establishing baseline performance. Relevant information includes bus length, the number of passenger seats and total passenger capacity, the number of buses in the fleet, the fuel type and engine technology, projected or scheduled annual total activity, and the scheduled annual activity per bus. These numbers are useful in a later step when information about buses and the routes are combined to generate energy consumption estimates, and soot-free and zero-emission bus technologies will be benchmarked against the baseline performance of these buses. The routes that buses operate on are as important as the buses themselves, which is why we also need to understand the route characteristics in the table below. The GPS data to collect for route characteristics include the length of the route, average speed of buses traveling on the route, the average number of stops per kilometer, the number of buses serving that route, and the number of total trips per day. The characteristics of bus fleets and routes that are collected in the previous two steps can then be plugged into a computer algorithm to calculate a drive cycle that's based on real-world bus operations data. Buses' operation conditions, from the weather to the speed and terrain, can be different from city to city, route to route, which is why this real-world drive cycle is extremely important. Instead of an arbitrary, generic, and sometimes unrepresentative duty cycle developed in a laboratory, the real-world drive cycle is more representative and truer to real operating conditions of buses and their energy consumption. The distance of a route, average speed at which vehicles travel, number of stops per kilometer, percentage of time that the buses are idle, and kinetic intensity, which, like I mentioned, a measure of drive cycle kinetics reflecting how much stop and go is in the cycle, are all very useful insights for the subsequent analysis that compares cost and range and projects minimum technical requirements and infrastructural needs for the technology transition.
With the representative drive cycle developed, now we can simulate the energy consumption of different bus technologies under different operating conditions, and then compare it against the actual fuel consumption of the baseline fleet. Energy consumption is arguably one of the most important considerations for operators when they plan their operations, and this prevents operators from taking uneducated investment risks. You can see from the figure above that for a set of different drive cycles, there are obvious gaps in energy consumption measured in terms of kilowatt hours per kilometer across different engine technologies: diesel, CNG, diesel-electric hybrid, and purely battery-electric buses. As there are more stop-and-go events in the test cycle, that is, the test cycle kinetic intensity goes up, hybrid and battery-electric buses save even more energy. Energy saving will be greatest on routes with the highest kinetic intensity. Apart from the energy consumption modeling, we'll also be able to use the fleet-wide planning framework to compare the total cost of ownership of different bus types at individual route levels. The cost can be broken down to vehicle acquisition, infrastructural acquisition, fueling, maintenance, staffing, and other miscellaneous costs. The bar chart here compares battery electric buses with and without air conditioning versus diesel buses with air conditioning. Additionally, we can also factor in the social costs of air pollution and climate change, two very important negative externalities that have oftentimes been overlooked in transportation planning, but are now receiving increasing recognition and are priorities in cities across the world. With social costs factored in, the case for soot-free and zero-emission bus technologies becomes even stronger.
It is also possible to compare route level TCOs in different scenarios by doing what we call a sensitivity analysis, such as air conditioning versus no air conditioning and different passenger loads. From a more strategic point of view, it would also be valuable to analyze the total cost of ownership under different battery electric bus incentive schemes, different interest rates, ownership periods, and energy prices. All of these analyses provide useful information to understand the best business and operational decisions for the technology transition. So what does fleet-wide planning mean in practice for bus operators? First, it makes route selection intuitive. This graph shows a comparison of estimated range, and daily utilization indicates which routes are most suitable for one-to-one replacement. Buses with a BEB range greater than their daily route utilization can more safely replace